Hi everyone, welcome to my channel, and in today's video we are going to discuss about the stock exchange system. So all of us might be familiar with what a stock exchange is. In India we have NSE, we have BSE, National Stock Exchange, Bombay Stock Exchange. In US we have Nasdaq, we have New York Stock Exchange. Similarly we have Singapore Stock Exchange. So most of the countries have their own stock exchanges where people buy and sell shares. So today's video is dedicated to the system design of such a stock exchange. Now you might be curious that why did we pick this system for our upcoming videos? So there are some challenges in building such a system. Let's discuss about those challenges. Definitely it's a financial system. It must be built with utmost care. Second, we need to scale it to the number of sells and buy orders. Right now people have started doing investments quite a lot, and these systems, these stock exchanges, receive a lot of buy and sell orders every second. So we have to build a system that is very scalable. Second, the system must support fairness. For example, if you're a retail purchaser or you're a retail seller compared to a HFT, the high frequency trading companies. So your stock exchange should support fairness for both type of clients. Second, we need to provide essentially fair market values for limit orders. For example, if I have set the limit order for my order, I should be able to get the best price for that particular order. So I somehow need to find the most or sorry, the best possible match for my order. And second, as we discussed match in the last case, right, we need to build a matching engine for stocks being sold and stocks being bought, right? So as part of this stock exchange, we have to handle a lot of these scenarios. We have to handle the financial aspect, we have to handle the scale, fairness, limit orders, and building this matching engine, which is the heart of this stock exchange. All right? Okay. So as we always start, right, we build a very high level system. We consider most of the services as a black box, and then after we design this system, then we drive our interview as per that system, right? So let's build the high level design of this system. Now we have two interfaces as part of a stock exchange. We have clients. These clients could be retail clients, these clients could be HFTs, who essentially call the buy stock or sell stock API for the stock exchange service. And on the other side, there is another interface where the stock admin portal should essentially list stocks or delist stocks from the exchange. Right? So for this black box, currently which we are seeing as a stock exchange service, it has two interfaces, one for the clients to buy and sell stocks, and other for its admin people to list and delist stocks. Right? So I think we are clear as part of the agenda of this slide that we wanted to cover why stock exchange is challenging as a system and what could be the very high level design diagram for a stock exchange service. Now, after some time, we'll peel off the complexities one at a time and dive deep into this black box system and come up with a more detailed system design for the stock exchange service. Okay. Let's move to the requirements. Like, what sort of requirements do we want to support? So, we have the high level system design which we created and came up with in the last slide. And using this high level design, let us come up with some set of requirements. As you all know, that we have two type of requirements, the functional requirements and the non-functional requirements. Let's start with the functional requirements first. So mostly if you are asked this question in an interview, the interviewer would be interested in the functionality of selling and buying stocks or tickers as part of this stock exchange service. So that is the P0 or key functional requirement for us. Second, we would be serving limit orders. So users would be specifying the price for buying and selling stocks. Next, orders are served till the market ends. For example, if I created an order today, and that order would only be valid till the end of the market, so it won't be valid or carry forward till tomorrow, right? So that is a key factor. So if I created an order at 9 a.m. in the morning, my order will still be valid if it's not matched till 5 p.m. till the market gets closed. Post that, my order would be failed. And as we have said that there is a fixed time for which the market runs, the payment integration is through third party providers like Stripe, etc. And another key factor is we should allow partial matching of the orders. So we should go once again over the functional requirements. Key feature is buying and selling stocks. Users provide the price of stocks they are buying and selling at. Limit orders is something we are going to support. Orders are only valid till the market end time on that particular day when the order was created. Markets are only active for 10 hours during working days. Payment integration is through third party providers, and partial matching of orders is allowed. Partial matching of orders, as in, if I am buying 5 stocks, someone is selling 10 stocks, then the person who is selling 10 stocks, his order is partially fulfilled. That is, only 5 of his stocks are sold. Similarly, on contrary, if I am buying 10 stocks and only 5 stocks are being sold, so my order could be partially fulfilled that I might be able to buy only 5 stocks because only 5 stocks are being sold. So partial matching of orders is supported here. Whenever you're coming up with such a system, right, you should always come up with some out of the scope scenarios which are mostly part of some mature uh, high customer base systems. Like in this case, there would be some notification service, some analytics service, some services that update the price candlestick mark for each stock, some scope of listing and delisting stocks, right? So all these things as well you should come up with, but you should essentially mention them that you would be able to cover them if there is time left in the end, but you'll make your design such that your design is extensible to incorporate these use cases. I think the functional requirements are clear to us. Let's move on to the non-functional requirements. As part of the non-functional requirements, since such a system has huge buy and sell scale, right? And it's a financial system and a lot of money is at stake. We can't make this system unavailable, right? The system has to be highly available as well as highly consistent. And we also discussed above about the trade fairness. So these three are the key non-functional requirements which we should satisfy. In addition to, the interviewer should mention or you should ask from the interviewer about the scale. In our case, let's say we are receiving 60,000, including both buy and sell. We are receiving a total of 60,000 orders per second, and the total number of stock companies that are listed on the exchange are 1,000. Let's say this is the scale that has been given to us. Now you are understanding this system has a total order buy sell TPS of 60,000. So that has a 60,000 TPS. Right, in airline reservation system, our TPS was 1. Now it has a 60,000 TPS. That's a huge TPS, right? So we need to satisfy this scale. That's why initially we mentioned that scale is a challenging aspect here in this problem, right? So when we are discussing about non-functional requirements based on scale, this system should be highly available. And since money is at stake and money of a lot of people at stake, it should also be highly consistent and the trade fairness aspect, right? So I think we are very much clear on the functional requirements of the stock exchange service. We are also clear with the non-functional requirements of the stock exchange service. We are also clear with the high level design diagram of the stock exchange service and some challenges involved, right? So that's a fair start for solving this problem. Let's see how we peel the complexities one at a time. Okay, so let's estimate the capacity for our problem, right? So before estimating the capacity of the problem, we should ideally come up with some specific database schema, as we have mentioned here, and some specific API contracts. And then based on the database schema and API contracts, we will estimate the storage estimates and TPS estimates, right? So the reason we have not mentioned TPS estimates, because the interviewer himself or herself mentioned as the TPS, like 60K per second is the TPS for our service. So that's why we haven't covered the TPS estimates, but we still wanted to cover the API contracts here, database schema and the storage estimates. Okay, so let's start with the database schema and cover each of these tables one by one, right? So at the start, we get an order request. An order request could be a buy order request or a sale order request or a sell order request, right? So an order request could have an order ID, which is our primary key. Let's come back why we have taken is at a partition key as well for later time, right? So an order request has an order ID. The customer who raised that order, the stock for which that order was raised, the quantity of the stock that we want to buy or sell, the price per unit at which we want to buy or sell, the type of order, whether it's a buy order or a sell order, and then finally, what is the status of the order? Is it failed? Is it raised or in progress? Is it completely filled? Is it partially filled? Why we have taken that completely filled and partially filled? Now you can remember that we support partial filling of orders, right? So this is an order request which the customer raises as part of our stock exchange, right? And then primary key is the order ID for this table. I'll come over the partition key after storage estimates, but let's keep your horses on hold for some time. Okay. Now, once an order has been raised, so what would happen next? Definitely there will be some matching between the orders. So there would be something called matched orders. Matched orders would have a match ID, buying order ID, reference to this, selling order ID, sale quantity, how much quantity is been bought and sold, and at what price that sale has happened, right? So that is a matched orders database schema. And then what do we have? We have the stock details, right? So this is stock ID, stock name, a lot of those stock metadata fields that is part of this stock details table. I just added it probably for the current design is not that critical, but definitely such sort of system would be there. In addition to it, there would be other tables as well, like user metadata, customer metadata tables. There would be other details like payment request details and all those things, right? So probably those tables are not that critical as part of this discussion. You can ask your interviewer if he or she wants you to go into those details, but I would say some two, three database schemas which are critical for your design, you should definitely design as part of your interview. Now we have designed our database schema, right? Let's estimate the storage capacity required for storing data as part of this table, right? So let's estimate for order requests table, right? Let's say this entire single record is 100 bytes each, right? We receive 60,000 requests per second. There are these many seconds in a day and 365 days in an year. So for a single year, if you multiply all these things, then we should have our answer, right? That's coming around 100 TBs of data for 1 year. So probably around 500 TBs of data in 5 years, right? So that's how you should calculate. Now, in an interview, you don't have time to essentially multiply all these things, right? You should take some sort of shortcut. Like I'll tell you how I would calculate in an interview. So I have 60K, right? Now let's imagine I move the 10 here and this one becomes 1000 bytes. So it's 1 kb. 1 kb into 6k. Okay, let's move the k also to the left. So it is 1k kb. So 1k kb is 1 MB. So it's actually 6 MB for us, right? Now we have 86400. Can we imagine is 10 is power 5 and this 10 is power 3, right? So we have 6 into 10 is power 8 MB, right? Now if we multiply MB by 1000, it becomes GB. If we multiply GB by 1000, it becomes TB, right? So out of this 10 is power 8, we took 6 zeros and converted our MB to TB. Now from those 10 is per 8, we have 10 is per 2 and 6. So it's like 100 to 600 TBs per year that's actually coming out as, right? So now you have an idea. Okay, I have hundreds of TBs of data scale as part of my estimates, and you can multiply it by 5, take some 20% growth in year, and you can come up with 5-year scale for that, right? But don't go and start doing the manual multiplications. Just take a very high level estimates like I did, and definitely you should always remember that your kb is multiplied by 1000 is MB, is multiplied by 1000 is GB, is multiplied by 1000 is TBs. So you should do those calculations very quickly. Always estimate this number of seconds in a day as per 5. So a lot of your calculations as part of these capacity estimates will be much faster, and you would save quite a lot of time in your interview. Okay, now let's estimate. So matched orders, right? So if we have, if what could be the maximum? So you need to essentially estimate the capacity of the matched order. See, if all of your orders, right, that are coming here are getting matched, so ideally its scale would be half the scale of the order request, right? So if it's coming as 500 TB, probably its scale would be 250 to 300 TBs. So we can scale that, we can mention that as part of our interview, right? So the interview just wants you to get outside a rough estimate of what could be the size of each table, right? Now let's stock details. This is a very small table. This is mostly static mode change. This would be updated through list and delist APIs, right? So we have 100 bytes of stock details, 1000 stocks we have. So we have around 100 KB of data in the stock details table. So that's not too much of data for us, right? So we have the order requests. When the order requests get matched, we have the matched orders, we have the stock details, we estimated the scale of each of those tables. This is around 100 to 600 TBs, this is around 200 to 300 TBs, and this is in KBs. So we now know the database schema, we now know their estimates as part of a problem, right? Okay, now let's come back to the APIs which we are trying to build, right? So at a high level, there will be two very important APIs. That is the buy API, which takes the customer ID who's trying to buy, the stock the customer is trying to buy, what quantity and the price the customer wants. Similarly, the sell API, which also includes who or which customer wants to sell it, which stock it wants to sell it, at what price and quantity the customer wants to sell the stock. So these are the two very common APIs that would be required. Second, once there is a match between two order requests, right, there would be another service that would be executing the match, and that service would have an API, that is match orders, which would say that okay, I want to match this order ID with this specific order ID for this much quantity. So this API might not be directly customer facing, but one internal service should essentially be exposing this API for other services to call it, right? We might not need to cover that as part of the interview, but if you are also able to come up with such sort of internal APIs as well that are critical to your design, those add bonus points to your interview, right? And definitely once you have submitted your order request, you might want to get the order status as well. Like this was my order ID, and I might want to get the order status once it has been submitted, has been succeed, failed, or whatever be the case, right? So I think that's the part of our database schema, that's the part of our APIs, that's the part of our storage estimates, right? So now a problem which we started with, like designing a stock exchange service, we understood like why it is critical, what are the challenges there, what could be its high level design, and what are the functional non-functional requirements, what are the API schema, what are the database schema, what are the storage and TPS estimates. So now we have covered quite a lot. We have peeled quite a lot of complexity. Now we should come to the main aspect of the system design. How will we essentially design the system, right? So what is the final design? Like the black box which we covered initially as part of our discussion, right? The stock exchange service, we essentially want to peel down or zoom into that black box and understand what is part of that black box service, like how the stock exchange service looks like from internal. Okay, so let's start. We have a client, right? And this could be an HFT client, this could be a retail client that should ideally be giving a buy or sell order. Now since we have lots of orders coming, right, we need a load balancer and a distributed service, that's the NASDAQ service, which have multiple hosts taking these requests, right? So clients through a load balancer submit a buy or sell order, right? Now, since there are lots of orders coming in 1 second, like 60,000 orders coming in 1 second, we need to scale the service so that it's able to take that much amount of load. And since we want to scale this service to take that much amount of load, we need multiple hosts. And to manage those hosts, we need a load balancer. So I think the first three components are clear to us. So client through a load balancer makes a request to NASDAQ service. Now the clients have submitted a buy or sell request, right? After some validations, this NASDAQ service stores these requests in a database called order request database, right? So this order request would have the schema which we mentioned above, right? Now what sort of schema, so we discussed about the schema of this table. So we'll come back what sort of database do we want, what choice of database do we want here. So we can come back to that, but okay, let's think it now. So we knew that the data to be stored as part of order request is going to be in hundreds of TB, and then this data is going to be very huge, right? So we need a database that essentially supports sharding and partitioning inherently. So whenever there are such sort of requirements, NoSQL comes as a choice to us. But to disregard that, we might not need MySQL. Let's see if we need any asset properties, transaction guarantees here or not. So here we are not performing anything related to finances. We don't need any transactions. We don't need any asset guarantees, right? We're just storing the request details, right? So this database does not need to be a MySQL database, right? And also based on our scale and partitioning requirement, we might want to choose a NoSQL database, right? So ideally, I would have gone with a NoSQL database here, not a MySQL database, right? Now, the NASDAQ service stores these order requests here and their status comes out to be in progress, right? Now, this database would have some other API dependent on it as well. We were just discussing about the buy and sell API here, but users would be seeking the status of their order request as well from this database. Now, since those status seeking requests would be majorly on order ID, So we might want to partition this database on order ID. It's also the primary key of a database, right? So that's very critical to discuss the details about this database, right? So all the buy and sell requests are written into this DB, and all the status requests are the read requests from this database, right? So it's essentially a read and a write heavy system. We need a lot of scale. The data storage scale is very high. Read and write requests are very high. So a NoSQL database would be the best solution for it. And also we don't need any asset guarantees and other things here. Okay. So whenever the client submits the buy or sell order request, the NASDAQ service validates it and stores it into the order request database. Now, post that what it does. Now, I have received a buy request, I have received some sell requests, I need to do some matching. Can I do that matching in a synchronous manner? No, because I might have just got the buy orders. I might need to wait for sell orders to come to execute the match, right? So, post that, I can't keep the system synchronous. I somehow need to introduce async mechanisms into my system. That's where I'll add two queues, one for buy orders and other for sell orders. I'll keep them separately. Now imagine there is just one queue. So I'll explain why I've kept separate queues for separate stocks. But imagine that I have just one queue for buy orders, one queue for sell orders. So you understand two things, right? So the very first thing you have to understand is why I had to introduce queues here. Because I had to make my system asynchronous. Matching synchronously was getting very difficult because I might not have received buy orders, whereas I might have just received the sell orders. I might have to wait for the sell orders to come to match them with buy orders, right? So for that reason I have to introduce queues into my system. Also, I wanted to segregate the buy orders and sell orders into separate queues. That would have made my life much simpler. That's why these are the two reasons I introduced queues and two separate queues, one for buy orders to segregate them and one for sell orders. And why queues? To introduce the async behavior into my system. Now imagine there are two queues here, right? Now I am pulling from these two queues as part of this matcher service. So this matcher service is pulling from these two queues. Now what would be the behavior here, right? So if I have just two queues where all the stocks are fed in, right? That would not be a good experience, right? Because I essentially want to match Tesla buy orders with Tesla sell orders, Meta buy orders with Meta sell orders, Google buy orders with Google sell orders, right? So if I essentially have separate queues for each of the stocks, like Tesla has its own queue, Meta has its own queue, Google has its own queue for buy, and similarly they have their own queue for sell, then anyone who's pulling from Meta buy queues and pulling from Meta sell queues can essentially go ahead and directly match them, right? This would simplify our life quite a lot. And also we don't have that much number of stocks listed ideally on any stock exchange, so we can do that. We ideally have only 1,000 stocks listed, so we just need 2,000 queues here, right? One for each company. So this is a very critical part of the design. Why do you want to introduce async queues here? Why do you want to have separate queues for buy and sell orders? Why do you want to have separate queues for each of those companies? These three things are critical. Now, if we have discussed these things, now imagine NASDAQ service has stored each order into its separate buy queue and company, sell queue and company, and done his job. And that way the client who made that buy or sell request would receive an OK and the order ID to later query the status for. So this is one part of the workflow that has ended. The client makes a buy or sell request. NASDAQ service validates it, stored into the DB, and then stores into the updated queue. And once that order is successfully stored into the queue, The client has been sent an OK request with an order ID, which the client can later query the status for. So this part is done. Now, once we have the orders as part of our queues, we want to match them. We want to match them at the best prices available, right? Now, and at the best prices available. Now, let's see, this is a matcher service. This is a distributed service, and there are a lot of matcher nodes here. And for each of the queue, we have, let's say, two or three matcher nodes that are continuously pulling from that queue and see what all orders do we have. Let's say we have these three matcher nodes that are just pulling from the meta queue, or let's say two matcher nodes that are just pulling from the meta queue. Why do we need more than one matcher nodes to pull from each of those queues? Because if one of them gets down, the other one is still pulling from that, right? So we can ideally need more than one uh, matcher nodes to pull from the queue. It could be two or three matcher nodes for each of those stocks, right? So let's say for meta we have two matcher nodes that are always pulling from the queue at 5 seconds latency, or let's say at a 5 seconds frequency. So every 5 seconds there are two matcher nodes which are always pulling from the buy queue and sell queue. Another matcher node also pulling from the buy queue and sell queue. If one of them goes down, the other is available, right? Now, whenever this matcher nodes pull from the buy queue and sell queue, so this queue should be something like Amazon SQS, right? Where once a consumer has consumed the message, that message is not available to other consumer, right? So that visibility timeout concept is there because we have two or three consumers for each of those queues, right? So if one of the consumer has consumed an order from buy or sell, the other consumer should not be able to see that order from each of those queues, right? So that's why we should use something like Amazon SQS here, so that only one of the consumers here need to have visibility over the message, right? So two important points we discussed here. For each of the stocks, we need two or three matcher nodes. They must be pulling from these queues at some varied frequency. It could be 1 second, 5 second, 1 minute, etc., based on our scale. Third, the queue should be similar to SQS, where if a consumer has pulled a message, the other consumer should not have visibility over that message, right? Now see, once a consumer has pulled some messages from the buy queue, some messages from the sell queue, what would the consumer do here? So let's say the consumer pulls 50-50 messages or whatever messages are available in those queues, and at max 50 messages from both the queues. So the consumer tries to match them at their best price. So if I'm asking for $50, someone if selling less than $50, then I should be matched with that person, right? Similarly, if I am selling for $50 and someone is able to ready to purchase for greater than $50, then the seller should be matched with that. You're understanding? If I am buying for $50 and anyone selling for $50 or less is a prospective batch to be mapped with me, the buyer. On contrary, if I'm selling for $50, right, and anyone ready to purchase for $50 or more, then I would be interested to sell to that person, right? So those people should be matched with me. So this matcher service performs the matching logic here, right? So definitely there would be some some orders that would get matched and some orders that would not get matched, right? So the orders that did not get matched will again put back into those respective queues and again pull them. So it will make sure that uh, these orders essentially are able to find a match for them, are essentially able to find the best match for them, and we are able to match them. right? Now, uh, that's how we are essentially every 5 seconds these nodes go to the buy queue and sell queue, pull 50 messages from each of those queues, try to match them. If there are some matches, we'll handle them. If there are no matches, we again push them to the queue. Again, they are pulled from those queues, try to match them. If there are matches, we handle them. If there are no matches, we again push them back to the queue. So this way, the order which we raised will definitely be satisfied at the limit we specified, right? Now, let's say this process happened for the entire day, and there were few orders which could not find a prospective match at the end of the day itself, right? So the last time after 10 hours when this matcher service would run, this matcher service would essentially pull those messages and see that, oh, their expiry has been happened, right? Because this expiry was till the market close time. So those messages would now not be pushed back to the queue, and they would be expired, right? That's where we discuss that initial functional requirement that the orders are only valid till the market close time. And that's how it's handled, because uh, after the market close and matches service pulls those messages and they're yet not matched, so they would be marked expired and they would not be put into the queue again. So the next day the queue would ideally be empty at the beginning of the next day, right? So I think that's the case. And there are two three things we have handled here. So the 10-hour expiry of the messages till the market close, right? That's the best thing we have handled here. Second other thing we have handled here is the order should be matched at their best price, the limit orders, right? And how we have handled them, we pull them from the queue, try to match them. If they are not matched, we again push them to the queue, and that's how we try to match them, right? So we have handled the limit orders here in that way. The last thing that is left is the partial order matching. That how will we handle the partial orders here? Now, let's say I pull a buy order from this queue that is buying 5 stocks, and a sell order from this queue that is selling 10 stocks, and there is a match for 5 stocks between them, right? So only 5 stocks are matched, so the sell of 10 stocks are still pending. So what I'll do is I'll create a match in my memory for those 5 stocks. For the remaining partial 5 stocks order, I'll again put back to the queue, so that I'll check if the another partial order is essentially the other partial order is essentially be matched with something else, right? So there is a buy order for 5 stocks, there is a sell order for 10 stocks. They are matched at the price per unit. Now only 5 stocks could be sold, five other units could not be sold. So that 5 units partial order I again put back to the queue and handle it again. All right. So that's how we handle three things, right? Market time expiry, best price at limit order, and partial orders are handled this way, right? So I think how we are handling these three critical aspects is very important to discuss as part of this design. Now, let's say we have got a match. We will not, so we are essentially giving just single responsibility to each of these services. This service will just create a match. It will not execute the match. So it will essentially put all those matches in a queue, and there should be an executor service later that essentially handles the execution of these matches, right? Because execution is a big task once. So there are two very big tasks. See, matching is its own big task, and execution of a match is another big task, right? So we ideally should keep them separately. And the reason we added queues is so that system is already async, and then these two services should ideally be able to scale at their own pace, right? That's why, and people ideally not split this task. It's good practice to split this task between matcher and matcher executor, right? So yeah, that's what we did here. We implemented a queue in between. Matcher service whenever identifies a complete or a partial match, create a match and add it to the queue. The executor service should now consume those matches and execute them, right? Okay, so how would the executor service execute those matches, right? And then executing a match is sort of a distributed transaction here. We discussed completely about the distributed transactions in the airline reservation system, so we might not go into that detail here. But I'll just explain the executor service flow, that what all this executor service has to do for one match complete, right? The executor service will essentially have to ensure that the payment or the money is deducted by some other service. The executor service will have to ensure that the orders are marked matched in another database, which we were mentioning earlier, the matched orders DB. And there is one step which I have not mentioned here. So now some request, right, be it a buy request or a sell request, is partially or fully satisfied, right? So that people who are querying its status will get to know about its status, right? So this service should ideally update this order request database, that okay, it is either partially fulfilled or completely fulfilled, and what is the quantity that is fulfilled for this request, so that the clients who are essentially querying the status of their order will definitely get these details updated from this backend. Now this order has been executed, right? There would be other auxiliary services whom we need to convey this message. So we should also publish the message to some sort of multiple consumer services like SNS or Kafka, or a PubSub model like Kafka, which has multiple consumers. Now, why am I stressing on multiple consumers? Because this notification that a match has been executed might be needed for a lot of downstream services like analytics, notification, ticker update services. Like, so that's where we should publish those messages to Kafka or SNS, so that later if we are building those services could be easily scaled, right? So analytics, notification, ticker update we have not covered as part of this scope, but they're handling that they can be extended with the existing design, right? So that's the entire design where we are handling like buy, sell, and status update requests. We are handling like limit orders, partial order matches, order validated till end of market. We are handling distributed transactions to executors, right? Then we are making our system scalable for future services like analytics, notification, and ticker update. I think that's what the entire system design for a stock exchange sort of service is. And yeah, that's it. Uh, Thank you everyone for watching this video. Do like, share, and subscribe. Thank you, everyone.